Alright, okay, something's being blended in the background, so I don't know if you hear any, like, extra noise, but... So, Wiley homework number 2, this one, I got through it and, like, did it all and got it right, so... It was a good time. Alright, so this is, question 2. And they say, let's get, that's like ugly. Okay, so there are 2 compounds. There are 2 compounds, and they both have the same molecular formula, which equals C5H10O. And they both, let's see what else. They both, okay, so they both have strong IR absorption peaks, absorption bands, bands in the 1710 to 1740 reciprocal centimeters region. Alright, so compound A, the proton NMR data that they give us is, so there's a chemical shift of 2.55, and it's a septet, so I'm just going to write 7, it's a septet, and it's 1 hydrogen. Then there's a chemical shift at 2.10, it is a singlet, so S for singlet, and it has 3 hydrogens. There's a chemical shift at 1.05, it's a doublet, so I'm just going to put 2, and it's 6 hydrogens. And then they give us the carbon-13 NMR data. There's a chemical shift at 212.6, a chemical shift at 41.5, and a chemical shift at 17.8. So a couple things, just looking at this, the carbon data, because there's 3 different there's 3 different carbon signals. That means that there's 3 different kinds of carbons in this compound. And now the IR, which was 1710 to 1740 negative reciprocal centimeters, that equals okay, it could be a carboxylic acid, it could be a lot of different molecules that have a carbonyl group, but it's not. And I think I'm going to taste some hummus right now, so give me 1 second, that my husband made. It tastes delicious, I mean real good. Okay, but looking at this molecular formula, the C5H10O, there's only 1 O, so it's not a carboxylic acid. So it's either going to be an aldehyde, right, or a ketone. An aldehyde or a ketone. I got this from page 86, table 2.7 in the book, and here is a aldehyde or, right, carboxylic acid. So from that, because I know there's 3 types of hydrogens, I look at this and let me see, how did I figure out? Okay, so I already automatically know there's going to be a carbonyl group, right? So I just draw that in. because I know it's either going to be one of these, an aldehyde or a ketone. So I looked at this and I said, okay, there are 3 hydrogens and they have a singlet, right? There's 3 hydrogens that have a singlet. That means that they're not next to any other heterotopic hydrogens. So I guess there's a couple ways that could happen, but I just put it here because these are 3 hydrogens that are next to a carbon that has no hydrogens on it. And so they're only going to give you a single peak. Yeah, they're only going to give you a single peak. This signal will only give you a single peak. Then there is 1 hydrogen that's next to a septet, which means that it's near 6 other heterotopic hydrogens. So I put this H here to be that 1 hydrogen, and then I attach this to 2 methyl groups so that I have 6 heterotopic hydrogens next to this hydrogen. This is 1 hydrogen that's going to be broken up into 7 because it's next to 6 heterotopic hydrogens. And finally, there are 6 hydrogens that are, and the signal is broken up into 2 peaks. These 6 hydrogens right here are homotopic, so they're the same, and they're next to 1 hydrogen, so they break up into 2 peaks. Alright, so then there was molecule B, and that's proton NMR data that they give us. There's a chemical shift of 3.28. It's a triplet, so I'm just going to write 3, and there's 2 hydrogens. There's a chemical shift at 2.10. It's a singlet. I'm going to write 1, and there's 3 hydrogens, right? There's a chemical shift of 5.7. It's a sextet. I'm going to write 6, and it's 2 hydrogens. And then there's a chemical shift at 0.88. It's a triplet. There's 3 peaks, and the signal is for 3 hydrogens. And then they give us the carbon-13 NMR data. There's a chemical shift at 209.0, 29.5, and the 17.0 and 13.2. Notice when it's just 13 CNMR, not the DEPT, we don't get how many hydrogens are attached to these carbons, we just get their chemical shifts. And there's 1, 2, 3, 4 different kinds of chemical shifts, so I know that there's going to be 4 different kinds of carbons, right? I know there's going to be 4 different kinds of carbons. So, again, we know that there's going to be a carbonyl group. It's either going to be a ketone or an aldehyde. So looking at this, I need 4 different kinds of carbons. There can't be any real symmetry in this molecule. And what am I going on? Blah, 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 blah. There needs to be a 2H that's next to 2 other heterotopic carbons. There needs to be 3 H's that are next to no heterotopic hydrogens. There needs to be 2 H's that are next to 5 heterotopic the hydrogens, because the peak, the signal is broken up into 6 peaks. Alright, so here there's a couple different ways, but I thought about it, and there's 3H. Oh, what? What am I talking about here? No. Let's figure. There's 3H. There's this 3H peak that's not broken. It's peak. This signal is not broken up into any peaks. It only has 1 peak. So I just put it here because that's a likely place that it would be. It's not next to any hydrogens, any heterotopic hydrogens. So then I had a 2H that was a 2H signal broken up into 3 peaks. So I put a CH2 here next to a CH2. These, and then I just put the CH3 here to make these heterotopic, to make these, where am I, blah. I put, right, this CH2 is next to these 2 heterotopic carbons. They're heterotopic, I think, because they are attached to this methyl group. This doesn't have a methyl group attached to it, so they're not the same. They're not the same type. They're not the same type. If you replace one of these hydrogens with a chlorine, if it was here or here, the molecule would have a different name. That's how you know that they are heterotopic and not homotopic. So this CH2 is represented by this, yeah, CH2 is represented by this 2H right here that's broken up into a triplet. It's also the hydrogens that are closest. They have the greatest chemical shift downfield, so they're closest to the electronegative oxygen, right? They're closest to the electronegative oxygen. This CH2 is right here. It has to be next to 5 heterotopic hydrogens, and it is 1, 2, 3, 4, 5. And then this CH3, which is completely upfield, it's the farthest away from the electronegative element of oxygen, and it's broken up into 3. That means it's next to 2 heterotopic hydrogens, and it's the farthest away from oxygen. So this was my molecule, and I got it right in Wiley, so we know it's right. Alright, so we'll see. Actually, this is enough for tonight, because I got other stuff I gotta go to, like a birthday party. Bye.